It's a great pleasure to be back in Edinburgh for me, especially to be at the International Science Festival, which is, you may know from the posters all over the city, that it has the theme of life, the universe and everything. Well, no one can accuse the festival organisers of being too narrow-minded, that's for sure. And tonight's session, this one, I think is going to do full justice to its breadth of ambition. We're talking tonight genuinely about things that encompass the whole universe, everything material in it, and how, by the nature of the mechanisms that govern that universe, how life came to be and we came to observe the universe itself. Science. What is science? Well, a few years before Einstein passed away, 1955, he talked about what he called the miraculous order of the universe. And he didn't apologize for using that word miracle. He was writing to his friend Solovine. The order that is essentially the providence, the province of scientists to understand that order. But there are lots of gaps in our understanding of that order. That's what scientists do. They work to fill those gaps. And tonight we're looking at two of the biggest of them. They go by the name of dark matter and dark energy. And we'll be making, I hope, clarifying the meaning of those two things, which are really quite different, and how we can seek to understand them in the next hour and a half. I should say that this slightly strange mystery, these, because dark energy, dark matter, astronomers, scientists, we're pretty well certain that they're there, but we don't know what they are. It's not total ignorance, but we're feeling our way to an understanding of something that we're only grasping dimly. Donald Rumsfeld might have called them unknown knowns. Now, the panel that is going to shed light on this on these topics is extremely distinguished, and we'll be looking at the problems themselves, the prospects for solving it or coming to a better understanding in the coming decades. But I just wanted to take a couple of minutes to just look back at the perspective of this in science. I'm not going to go all the way back to Aristotle, but I just wanted to look back to a situation in this city a few decades ago. To be precise, 79 years ago, on the 6th of February 1939, when the great theoretical physicist Paul Dirac gave a talk on the philosophy of physics less than a mile away at the Royal Society of Edinburgh. Now, Dirac was very much a physicist, not a philosopher, but he was persuaded by Max Born, a refugee theoretician based in Edinburgh, to talk about the philosophy of physics. And he made some comments in that talk, which is one of the classic talks made by scientists in the 20th century about looking to the future of their subject. He made several sweeping statements. One of them was partially surprising, perhaps. He said, in his matter-of-fact way, that the greatest developments in physics in the century so far were quantum theory, theory of the very small, theory of atoms, relativity, theory of space, time, gravity, and he added cosmology. Towards the end of the talk, he made a statement that may have taken some of that audience by surprise, because he said, and I quote, "Cosmology will probably turn out to be philosophically even more important than relativity and quantum theory." And I think that after tonight's event, you will have some appreciation of just how far-sighted that comment was. Strange that it must have seemed at the time. Our panel. My left, Michaela Massimi, who's a philosopher here at the University of Edinburgh. Ofer Lahav, the University College of London. Katie Roma, University of Sussex. John Peacock and Alex Murphy at the University of Edinburgh. And this whole session has been made available by funding from the the European Research Council, and we'd like to extend our thanks to them for their generosity in funding the event. Just to say that we've got just under an hour of talk here on stage, so to speak, and then there's a good half hour of questions. So if you have any questions you're willing to ask, no matter how simple they are, the simpler the better in many ways. I mean, this is about really basic approaches to cosmology. Then I'll do my best to fit in as many as we possibly can. We'll start off with a question to each of our, if I may call them, panel. Starting, if I may, with Kathy. So, Kathy, what is dark matter?
Now, Graham, I have my notes prepared, but listening to you made me realise, do you know what dark energy is? I mean, dark matter?
Dark matter.
It's an embarrassment. That's what it is.
Oh, thank you. That's very helpful. Go on.
Well, 1933 was the first time when dark matter was proposed by Franz Zwicky, studying actually my very favourite type of object in the universe, clusters of galaxies. And we still don't know what it is. Mm-hmm. And so it's an embarrassment. But going back to the script, I will answer your question, a distinguished chair, in two ways. The first way is I'm going to say that dark matter is a tangible thing. It's something that exists. We just don't know what it is yet. And the second thing is I'm going to say, well, it's a construct. It's an ansatz. It's an idea to explain stuff we don't understand, we can't explain in other ways. So I'm not a philosopher, old-fashioned astronomer, like my telescope, so I'll concentrate on the first thing. So we're on the page that dark matter is a thing, it does exist. So what do we know about it? Well, it's dark. And what do we mean by dark? Well, we obviously can't see it with our eyes, but we couldn't see it if we had X-ray specs on either. It doesn't give off radiation at any wavelength anywhere in the electromagnetic spectrum. And the universe is a fabulous place. I started off as a physicist, became an astrophysicist. What I love about astrophysics is that there's physics everywhere in the universe, and it produces radiation at all wavelengths, from radio all the way to gamma rays. Dark matter doesn't do any of that. So how do we know it's there? Well, it's matter. That means that it has mass. That's what we mean when we say matter. So anything that has mass has an attractive force through gravity. And so it does stuff. So we see what it does, we just don't see it. So there's something else we know about it. And that's that there has to be a lot of it. Really loads of it. And one way you can imagine it is if there is dark matter, and it's made up of a particle, and Alex is going to be talking about particle explanations and detections of matter, dark matter soon. There'd have to be 1 trillion dark matter particles moving through your body every second for the universe to be the way it is at the moment. So that'll probably freak you out. But then you can put that into context, because that's actually 10 trillion, actually 30 trillion bacteria in your body right now. So there you are. And the bacteria aren't going anywhere, but you've got 10 trillion dark matter particles coming through you. So we know that there's a lot of it. We know that it's dark. We can also infer that it's not sticky. By sticky, I mean that when two dark matter particles pass each other, either in your small intestine or in the outer space, they don't know anything about each other. They're like ships passing in the night, old-fashioned ships with no radar. Because if they were sticky, they would give off radiation. Maybe they'd rub against each other, they'd get hot. No, they don't do anything. They ignore each other. So the last thing we can infer is it can't be anything familiar. All right? Normal stuff, all of us, the Earth, the Sun, is all made up of basically neutrons, protons, electrons, and you've probably heard of photons, neutrinos, maybe some more exotic particles. I know everybody in Scotland has a fantastic education, but we focus on protons, neutrons, electrons for now. You could collect up an awful lot of them and dump them into one place, and for that to have a really large gravitational field, and for it not to give off radiation. Now, if you put up too much, it becomes a star. You don't want that. Jupiter, right? Jupiter's a great big collection of normal stuff, and once it cools down completely after formation, it'll be dark and cold. It could be dark matter. Unfortunately, you can't defy the laws of physics, and you can't make a universe the way that we have a universe now if dark matter is made up of normal stuff. So it's dark, it has mass, it's not sticky, and it's not normal. So that's basically what I want to say on that. And then in terms of the other one, the philosophy, 2,000 years ago, Ptolemy suggested that you could explain the motion of the planets in an Earth-centric universe, so that the Earth is the center of the universe, using something called epicycles. And these epicycles would predict very accurately the positions of the planets, what was going to happen in the future, etc., etc. So it was a perfect model, except for the fact it was based on an incorrect assumption. So I'm wondering if in 2,000 years, or even in 20 years, the next generation of astronomers will look back at dark matter with as much mirth as we do about epicycles. So that's a bit of a long answer, I'm sorry.
No. I like we begin with an embarrassment, though. Mm-hmm. Okay. John, so we've heard about dark matter. What is dark energy?
The most important thing you need to know about dark energy is that it badly needs a different name. Most people here have probably heard about E equals mc squared from Einstein. So energy and matter are just two different names for the same thing, stuff. So dark matter and dark energy logically have the same meaning. But actually, as those terms are used in cosmology, they couldn't be more different. So what are the main differences? Dark matter, the stuff Kathy's been talking about, clumps under gravity, as does ordinary matter. We're here today courtesy, in part, of the gravitational field of the Earth that's keeping us from floating off into space. And galaxies, larger structures in cosmology, are built up partly out of ordinary stuff, partly out of dark matter, and that keeps the stars in their orbits around the galaxies. Now, dark energy is a name to say that there's some extra stuff in the universe that isn't capable of clumping in the way that everything else that astronomers look at does. So it's spread completely uniformly throughout space. In fact, you could think of it, and sometimes this is a term that people use interchangeably, as vacuum energy. It's what's left over if you take this room, take all the air out of it, and hold your breath so you don't suffocate. Have you got a vacuum? You've got emptiness. Well, emptiness weighs nothing, obviously. But that's empirically not the case in cosmology. Observations, that I guess we'll get to discussing in a bit later, have told us that there seems to be uniformly spread throughout space, filling the space between the atoms, if you like, this extra substance. Now, there's very little of it. The amount, it's here in this room, it's filling the whole of this lecture theatre. But the amount is pathetically small. If you take the entire volume of the Earth, though, then Alex and I were just talking about this, and we agreed that there's roughly 1 milligram of dark energy, or the mass equivalent of the energy, is in the entire Earth, is 1 milligram. So it's such a small fraction of the Earth's total mass that it's only on a much larger scale of cosmology that you can actually detect it. So first important property is needs a different name. Second important property is doesn't clump, but that doesn't mean that it's immune to gravity, because the third important property is that its gravitational properties are actually backwards. If you want to dramatize it, you would say that dark energy is anti-gravity. At this stage, we probably better just accept that that's the way it is, because that's what we observe, and B, because it's actually a consequence of the relativistic theory of gravitation that Einstein invented in 1915. So if dark energy exists, if the whole of space between the rest of stuff is filled with some density of this material, instead of making the expanding universe slow down its rate of expansion, making the galaxies as they separate from each other separate at a lower velocity, in fact it causes the opposite. It makes it speed up. And this is something that was observed, well, the observations really hardened progressively over about 10 years in the last decade of the 20th century. And really now, there's so much evidence that nobody disputes this. We're in an expanding universe, everything's getting further away from each other, apart from this room, obviously. It's a Woody Allen film, I talk about this. The kid says, oh, he won't do his homework because the universe is expanding, so there's no point. And the mother says, oh, for God's sake, we're in Brooklyn. Brooklyn is not expanding. So this room is not expanding, but the universe as a whole, stuff's getting further away from each other at an increasing rate. And that observation, allied with Einstein's theory of gravity, tells us there must be something filling space that's doing the pushing. Okay. What is it? Same story as dark matter. Well, we can't say we don't have the faintest idea. We've got far too many possible ideas, and the difficulty is distinguishing them. But let's just talk about maybe two. If you think of dark energy as being the fact that the vacuum itself has some stuff in it, how could that make sense? Isn't just emptiness emptiness? No, from the point of view of quantum mechanics. So quantum mechanics, the physics of the very small, one of its characteristic features is a kind of intrinsic uncertainty, a randomness in nature. Heisenberg coined the term the uncertainty principle, which basically says it's impossible to have complete knowledge of what's going on at the microscopic scale. For example, you can't, if you take an elementary particle like an electron, Heisenberg would have said it's impossible to know precisely where it is and precisely how fast it's moving at the same time. Interesting. So if you take an atom and you make an atom smaller and smaller, so you know exactly where that electron in the atom is, it has to move faster. And so you can't make an atom below a certain size, otherwise the electrons would have to move at the speed of light. And that's more or less why atoms are the size they are. We're made of atoms. Atoms can't shrink, otherwise we'd all collapse to nothing. So quantum mechanics is all around us every day. So in the same way, complete emptiness can't be completely empty, because that would be a perfect state of knowledge. And the way we express this is in terms of things that physicists call fields. And fields are yet another thing that nobody actually knows what they are, really. They're just there. So a familiar example is the electromagnetic field. We're seeing each other by light, and what that means is there's a thing which you can almost think of as like connecting the light with a little elastic string and shaking it, and ripples running up and down the string. And that's what light is. That's what the great physicist, Scottish physicist Maxwell taught us in the 19th century. But quantum mechanics says that those strings can't be completely stationary, because that's a state of perfect knowledge. So just the fact that there's light, even if you turn all the lights off, you can't turn it right down to zero. That's one reason why the vacuum should have some weight. So there are other things. I'll just mention one, since, again, where we are, we would have to talk about Peter Higgs. I'm sure he's going to come up sooner or later. There are plenty of other things that are a bit like light, but also quite different. And one of these things is the Higgs field, whose existence Peter conjectured in the 1960s and was finally found at the particle accelerator in CERN a couple of years back. So things like the Higgs field could also give weight to empty space when you've taken all the particles out. But there are many other possibilities, and figuring out which the right one is a matter I guess we'll return to.
Okay, just before we go on to our next question, you talked about the need of a different name. I think most people would agree with that. So that we can keep it in our minds. You don't like the term vacuum energy.
Oh, I do. No,
okay,
if given the choice, that's probably what I'd choose.
Okay, all right.
Except technically, vacuum energy tends to be used for something that's characterized by just one number, as it's the same not only everywhere in space, but everywhere in time.
Yeah.
It was also sometimes,
okay.
Einstein invented this in 1917. He called it the cosmological constant.
Right.
Does what it says on the tin. It's
well, let's just keep that simplicity in mind, because we're going to talk about...
But dark energy really means something that number might change with time, for example.
Yeah. Okay, good. Well, thank you for that. So, Ofer, how do we actually look for this dark energy that is everywhere and elusive?
Right, so we had excellent introductions by Kathy and John on what is dark matter, what is dark energy. We should say that, to go to the bottom line, there is a consensus, surprisingly a consensus, in the entire community that at present, if you think about a pie diagram or a cosmic budget or a cosmic cake, only 5% of the stuff is actually ordinary matter.
Stuff like us, you mean?
Like us, like this flower and the water and us. This all comes together to 5%, only 5%, and then 25% in the form of a mysterious dark matter, called dark matter, probably, and the 70% is dark energy. So it's in a very, talk about embarrassment, it's really strange, right? There's only 5% that we can grasp, even not all of that is actually seen. And we live in a universe with 95% of darkness. I don't know, Graham, if it's a known unknown or an unknown known. I'm not sure. And I would say, given this excellent combination here of scientists and philosophers, there's a nice quote from one of the Apollo 11 astronauts, Collins. He said, next time we come here, we need a poet, a philosopher, and a priest to tell us what does it all mean. And I feel that maybe to some extent we are in that situation, right? All the observations point at this universe, this very strange combination. Astronomers are happy with it, give or take. But what is it? So how do we actually measure it? Why did we come to do it? So it was just mentioned, Einstein wrote a very influential paper in 1917, just over 100 years ago, where he introduced a letter, a Greek letter called lambda. Why did he put it there? It's an interesting question. He had actually some issues about stability of the universe, but then he used it to argue the universe is static, neither expanding nor contracting.
But he thought it was static, didn't he?
He thought it's static, and then Einstein discovered the universe, Hubble showed the universe is expanding.
But that was later.
Later, no, but not much later, and allegedly,
Actually, it wasn't Hubble.
well,
You know, I have some things on that.
observers, and it was valued by Hubble. See, history is, that's why we need historians. But in any case, there was clear evidence the universe is expanding, and allegedly Einstein said it was his biggest mistake. So it should be zero. Then over the years, there's a very checkered history of that. Lambda came back each time we needed more of something. That's another way of thinking about it. When you need more, you need to make the universe older. You put lambda in, you get an older universe. If you need more volume, you put lambda in, you get more volume. Let's say if we take a snapshot 30 years ago, I was then a PhD student in Cambridge, lambda was categorically zero, no dark energy. It was 5% ordinary matter, 95% cold dark matter. So what made that paradigm shift? What made it shift? So there was this critical, although people suggested it over the time, as I said, each time there's something missing, this critical observation in the late 90s of two teams that look at distant objects called supernovae. Now we think that nature was kind enough to make them all look standard, or we also have a procedure to standardize them. So it's a bit like looking at street lights. Imagine they're all made the same factory, just the same. You could tell the distances. You can tell that this one is further away than the other. And that was what actually this discovery showed, that the model at the time, which assumed no dark energy, no cosmological constant, could not fit the data. Okay, these supernovae look dimmer than they should have in that model. People tried to find all kinds of issues as to physical issues that could explain it, but the Nobel Prize Committee in Stockholm was convinced that that's true, and they got the leaders of that collaboration.
Were you convinced?
Not yet. Not yet. I think it's actually almost too good to be true.
Wow.
That something so empirical gives this answer. So I have my skepticism actually about this measurement altogether.
Right.
But my esteemed colleague think differently.
Interesting. Yeah.
However, luckily, other techniques that help us to find the same thing. So these supernovae are what we call, it's not nice calling them standard street lights, so we call them standard candles. They're also standard rulers. And there's a feature in the galaxy distribution. If you do particular mathematical analysis, you can find particular scales. Right. And these actually have been detected. They come with a funny name, baryonic acoustic oscillations, in fact, detected in 2 surveys. John and I were in one of them, and John has led actually that discovery. Standard rulers. So that's second method. Okay, so we've got already 2. Then there are clusters of galaxies, which is Kathy's expertise, and it's just in a universe with or without dark energy, you'll find different number of clusters. I refer to the volume effect. So if you want more, you don't find enough clusters, just put dark energy there, you'll get more volume. But also it affects the way structure grows. And the fourth method is a very, almost again, sounds almost science fiction, and this goes back to Einstein as well. It's called gravitational lensing.
Yeah.
So light, as it passes through space, gets bended. So something which, if you put a coin, for instance, just circle, because the light goes through stuff in the middle between us and the coin, which is, say, galaxy, the coin, the circle would become banana shape. And as we call it gravitational lensing, there's strong lensing, beautiful arcs. I advocate, look at the Hubble Space Telescope website, you'll see beautiful arcs. And there are also tiny of those effects, which are called, it's called weak lensing. All these effects together are very important. There are many surveys doing it, dark energy surveys, one of them in future. So hopefully I answered partly at least the question, how do you measure it? How do you search for it?
And just very briefly, are you personally optimistic that we will have a better understanding of that in the next 5 or 10 years from these
understanding
observations?
or measurements?
Well, whatever. Well, both.
Okay, there are 2 things here. One is it's very impressive that you look at the literature, you look at the results by different techniques. We haven't quite mentioned the cosmic microwave background, which is its own patterns, which also agree with that. You look 4 or 5 different techniques, different groups, and they get the same answer.
Right.
We just published a paper of dark energy survey recently, and the abstract categorically says it is a cosmological constant. Yeah? Do I believe in it? Is this the end of the story? I don't know. Maybe we could be fooled like the epicycles. We might be fooled that we interpret it in that way.
Okay.
Maybe young, bright students would come and say, you've got something wrong.
It's interesting you put a little, margins of doubt in here. It's interesting that you're doing that here. You're not.
I think we must. It would get boring, right? Otherwise, if it's just this is it,
Okay.
And so it's one thing measuring it accurately and precisely.
Yeah.
There's 2 different things, accurately and precisely. And I think dark energy survey would get there, but then there's other projects coming up, both space and ground-based. By the way, each of them is about the next generation. But I shouldn't talk about money here. But these are big projects. It's like $1 billion, but each of them will produce billion galaxies or so. So you get $1 per galaxy. So it's not too bad.
Okay, maybe we move on because
we might move on.
No, it's a very positive note. All right, now just to be clear, let's go back now to dark matter, right? Which Kathy describes so vividly as an embarrassment, and how we might identify exactly what that is, where it is. So, could we have your view, Alex, on that?
Right. So, dark matter, the evidence for it so far comes exclusively from its effects, its gravitational effects. So it's or surveys of galaxies and things, and you look at how it appears gravity is behaving, and from that you infer that there's dark matter out there. And that looks to be consistent with dark matter being fundamentally some kind of particle. So what we're striving for is a completely different kind of measurement, not relying on gravity to actually see this stuff. And when we say see it, we kind of mean interact with it somehow. So there are various ways of doing it, but they fall, most of them, 99% or something of them, fall into 3 particular categories. And those are sort of colloquially known as make it, break it, or shake it. So the make it idea is essentially what's going on at various colliders around the world, but the obvious one is the LHC, the Large Hadron Collider at CERN. And so, coming back to something John said, Einstein E = mc², energy and matter are basically the same thing, with the scaling constant is the speed of light squared, a big number, turns out. And so if you get at the LHC, they've got protons whizzing around 99 point some serious number of 9% the speed of light in one direction, protons also going around in the other direction and slamming them into one another. You've got a huge amount of energy, and essentially you can just convert that energy into matter, is the aim. Now, if some of that matter that gets generated is dark matter, or a particle like the dark matter particle, then what's the effect going to be? Well, normally when you slam these two things into one another, the stuff that comes shooting out is normal matter, and it interacts with detectors that you put around it. So you can then appeal to another famous scientist, who we have to mention surely today, Newton. And so Newton has Newton's laws, and essentially the two that we're going to appeal to are conservation of energy and conservation of momentum. And we expect those physicists are really kind of very attached to those particular laws. That and the third law of thermodynamics are probably the ones that we really always want to abide by. And so if you have so much energy going in, you expect after the collision to be able to see that amount of energy come out again. And likewise with momentum, where it turns out you've got momentum of one proton going this way, momentum going the other way. Momentum is what's known as a vector quantity, so you have to take into account the direction. So beforehand there's actually no momentum because you've got equal momenta in opposite directions. So afterwards you should also see no momentum, net effect no momentum. So whatever flies out to one side, you should see an equal amount of momentum flung out to the other side. If you're generating dark matter particles in this though, the detectors won't see them because, as Katie said, dark matter just basically flows through the Earth, through us, through everything else without interacting much. So if you see these LHC type collisions where energy and momenta are not being conserved, that would be evidence that you've produced dark matter and made it. So that's the sort of first way of doing things. The second one, which I mentioned, was break it. And what we mean by there is essentially destroy it or allow it to destroy itself. So dark matter, we've seen it through its gravitational effects. So as it's affected by gravity, and it causes gravity, it has mass, wherever it's most dense is where it's most populous. And if the density is high enough, then one dark matter particle may one day meet another dark matter particle, and if the dark matter has particular properties, it may well annihilate. And then there's again E equals mc squared, and the mass that you've got of the two dark matter particles hitting one another and annihilating with one another can be transformed into photons or lower mass particles, neutrinos, various other weird and wonderful things. And then, so wherever there's very high densities of dark matter, which may be places like the center of our galaxy or the center of our sun, possibly even the center of the Earth, we may be able to see signals coming from those regions of things like high energy photons, high energy neutrinos, whatever. And there are telescopes in space and telescopes on the ground that, on the surface of the Earth that are looking for these radiations. Then there's the third principal method of trying to detect dark matter, which is the one that I'm in fact involved in, which is known as shake it. So you're actually trying to use the dark matter to come in and physically scatter off something. So we've got tens of trillions of dark matter particles flowing through us, through the Earth, and they basically flow through, but maybe occasionally they scatter and interact with stuff. It can't be that often, because if they did, then it would be warming up the Earth and things like that, and that in fact produces a limit on how strongly that interaction might be. So how do you go about doing this? Well, essentially what you want to do is build a big detector, because we know the rate is very small, and it's got to be incredibly sensitive, because we know that when this happens, it's going to, for slightly complicated reasons, it's going to be depositing very, very little energy. It's going to be a very light interaction. So we build super sensitive detectors and put them in places where we've shielded them from all the other types of radiation that we can imagine. So essentially there should be nothing happening in it, and if we suddenly see something happening in it with no obvious cause, maybe that's the dark matter scattering. So the ones I'm involved in, for example, typically use liquid xenon. So xenon is a noble gas, atomic number 54, discovered by a Glaswegian, William Ramsay. Americans, for some reason, insist on calling it xenon, but since we discovered it, I want to call it xenon. And so, essentially, we get a big bucket of this liquid noble gas, xenon, put it in a very dark place, turns out to be about 1 kilometre underground, and look at it. And xenon, why do we use this xenon? It's because it turns out to have a really nice property that when a particle scatters in it, it generates a small flash of light. So we essentially go 1 kilometre underground and stare for months on end at a bucket of liquid xenon, waiting to see a little flash of light.
It's such an exciting life.
Such an exciting life. However, why do we go a mile underground? Because we want to get away from cosmic radiation. So there's the sun, active galactic nuclei, lots of other things are generating high energy particles that slap into our atmosphere and generate various types of radiation. And so by going deep underground, we can get rid of, 999,000 out of 1 million parts of that. And then we build everything from hyper pure materials, because everything naturally has uranium, thorium, potassium in it, and those are faintly radioactive, so we want to get rid of that. We build it within sort of concentric shells of detectors so that anything coming from the outside, we can see it before it gets into the main volume. And it really is a fanatical level of passion towards cleanliness and trying to get rid of all this other radiation, so that if you see something happen without an obvious cause, maybe that's the dark matter happening. So that's what we're trying to do.
Right. Okay. So dark energy, dark matter. We've heard about the people doing this. We call them scientists. Two of the people we've heard mentioned tonight, great figures in the field, James Clerk Maxwell and Isaac Newton. They never called themselves that. They called themselves natural philosophers. To a certain extent, everyone working in this field is a philosopher of a type, and we've got a real one here, Michaela. So, Michaela, tell us about a philosophical perspective of dark matter and dark energy.
Sure. Well, obviously, cosmology is really a treasure trove for philosophers like myself who are interested in methodological and conceptual issues in science in general. And think of it, what we just heard is that 70% of all the stuff of our universe is made of dark energy, but we still don't understand what dark energy is. 20%, 25% is made of dark matter. Alex is involved in experiment to find it, but we still don't have any direct detection as of today. And so this is a treasure trove for philosophers, because we might be sitting on the verge of a scientific revolution. In a way, it reminds me of the early 20th century when Max Planck introduced the quantum postulate. And it really took...
Now, here you're talking about the fact that energy is being discrete, not continuous.
That's right. The idea that there are quanta of energy, and it really took the following 30, 40 years, and people like Bohr and Dirac.
That was a real revolution.
And Heisenberg, that was a real revolution to fully unpack the consequences and implication that hypothesis had for thinking about the nature of reality and physical reality. So we might be at the verge of a revolution like that if we find exactly evidence for dark matter, and if the dark energy survey is able to exactly tell us the nature of dark energy as a value of the vacuum. So from a philosophical point of view, these are some of the philosophical questions that we are interested in studying as philosophers. Questions about evidence, for example, in cosmology. Cosmology is very different from other areas of science where it's possible to run an experiment, repeat the experiment on more than one sample. We have just one universe to observe. And the data don't come forward.
Anyway,
look at that. Data don't come forward very easily. They're very difficult to harvest. So it's really interesting to look at some of the methodology that they use at the Dark Energy Survey and the New Generation Survey like DAISY and so forth to harvest those data. There are questions about modeling. So I was intrigued by what Kathy said at the beginning. She said it's tangible, dark matter is tangible. Obviously, those are questions about how we model dark matter at different scales. And maybe I'll say something about that. Questions about what are the problem and prospects of rival views that we haven't really been discussing so far. I mean, Ofer mentioned some, like a note of skepticism, maybe I'll say something about it as a kind of, philosophers love controversy.
Do you mean people who would fundamentally disagree with the existence of these things or different approaches?
That's right, people that are looking for alternative to dark matter and dark energy. So let me say, something briefly, very, very briefly, for example, on the problem of modeling dark matter. We have good reasons for thinking that there are dark matter, so I'm not going to be saying anything on dark energy right now, because we need dark matter to explain a variety of phenomena. So you may all be familiar with a phenomenon that has to do with individual galaxies. Take our Milky Way, our galaxies. It's well known and is experimentally measured that if you look at the rotational velocity of our galaxy, that velocity doesn't decrease if you go in the outskirts of the galaxy. Why is that? Well, if we believe that there is a dark matter halo and that the galaxies form inside the halo, then we have a natural explanation as to why the velocity stays flat, because it's kind of proportional to the, not just the baryonic content that we observe, but also with the dark matter halo. So that's one of the reasons that we have for believing in dark matter. The other reason is that we really need dark matter, as Kadi said at the very beginning, to explain galaxy clusters, not just individual galaxies like our Milky Ways, but why loads and loads of galaxies tend to cluster together, what holds them together, what is the glue that keeps them together. So if we believe in dark matter, we have a natural explanation of that phenomenon. And more generally, at the large-scale structure, if you've been at the museum here, at the Earth in Space section, you may have seen the video where all made of stars. So in that video, there is this beautiful picture from the WMAP. And I mean, it's a similar picture that come up in Planck that shows the fluctuation in the cosmic microwave background. So if we believe in dark matter, we have a natural explanation of how the universe evolved from those original fluctuations in the cosmic microwave background. Now, when it comes to modeling dark matter, from something like our Milky Way to cluster of galaxy up to the whole universe, the formation of the entire cosmos, this is where the interesting philosophical elements come in, because at the level of individual galaxies, for example, some critics of the current cosmological model, I'm going to mention them, people that defend what is called the modified Newtonian gravity, which is a view defended by Milgram in 1983, claim that we don't actually need to introduce dark matter to explain flat rotation galaxy. We can have an explanation of individual galaxies without dark matter just by modifying.
You don't need the concept then?
Yeah, just don't need the concept. Don't need to introduce the idea of this entity that we don't know what it is exactly. We can just do that by modifying the laws of Newtonian mechanics at the cosmological scale. So this is where the debate begins, because some critics, and they are a minority in the field, have made that point that maybe we shouldn't really be looking for dark matter. Maybe there is an easier explanation in terms of modifying the laws that we know and love at the cosmological scale. The reality is that as of today, those rival approaches haven't really been able to explain the great variety of phenomena that we observe, not just at the scale of individual galaxy like our Milky Way, but at the level of clusters of galaxies and formation of the universe. So we don't have a rival, we don't have a genuine alternative to the current model that tells us that there have to be dark matter and dark energy. We have a possible rival for dark matter at the level of individual galaxies, but not really anything similarly successful or powerful explanatory for explaining those other phenomena, those other scales. So
would they say that if they were here, do you think?
I think that's fair to say. I think there have been attempts at expanding MOND, for example, to explain a galaxy cluster. This is what is called EMOND or extended MOND, but they are nowhere near to have the kind of explanatory scope that our current cosmological model has. That's interesting philosophically, because on the other hand, there are phenomena that the current cosmological model can retrieve using computer simulation, but they are more naturally explained by the rival theory. So there are interesting questions here about retrieving data versus explaining data, questions about the increasing role of computer simulation in all this modeling activity that I've just described. So there's a lot of observation and measurements, but there's also a lot of using computer simulation in delivering those data.
Okay, right. Okay, now, ladies and gentlemen, I want to make quite sure that your half hour is protected.
Absolutely,
so I'm going to be quite brutal with our my friends on the panel, because we've taken more than our scheduled time. So if you'll forgive me, I won't actually administer corporal punishment, but I shall give some nasty stares if people go extend their time. So if you could be very brief on these next few questions, so that we give our audience plenty of time to speak. Now, Kathy has the biggest challenge. challenge because you've got a big topic which I would like you to address in 3 minutes, which is the broad changes in cosmology in the last 25 years. So without repetition, deviation, and all the other things, can you give us the big summary on how cosmology has changed in the last 25 years?
I'll try 3 minutes. I think actually Ofer touched on it, and the precision by which we could now measure certain numbers in cosmology has just changed dramatically. From when I was a PhD student here in Edinburgh 25 years ago, we were lucky if we could get a measurement within 100%. You know, if it was 10, it would be plus or minus 10. You know, that's not much knowledge. And now, you know, you're talking sub% accuracy. And so we can measure with a lot more precision, but I'm not sure that our understanding has increased a lot in 25 years. So when I was here, as Ofer said, the universe was made up of all matter, so it was mostly dark matter with a bit of normal matter. Dark energy didn't enter the equation. Neutrinos didn't have any mass. The universe was a simpler place. We used to talk about cosmology being the pursuit of 3 numbers, but now if you look at it, one of the most recent papers by the Planck team, Planck is a space satellite that studies the cosmic microwave background, they've got like pages of different parameters to measure. So it's a lot more complicated, but I'm not sure that the understanding has really moved forward.
But you said more accuracy and more precision, though.
Yes.
That's surely
so it's more like
the
epicycles in the sense that we can predict so many different things, but are we actually asking the right question? You know, so the fundamentals. I'm hoping for a big breakthrough in, like you said, in 5 years. But I think for me, the real shock is the way that we do our work. So when I was here in Edinburgh, we were lucky if we got 1 or 2 nights of telescope time. And those nights were so precious. If you had bad weather or something wrong with the instrument, I remember the devastation of having a clouded out night. And now, Ofer and I've been working now, John as well, for many years on the Dark Energy Survey. You know, I go down for a week. If it's cloudy, I'm like, fine, I'll just go and, you know, do my email. And, you know, so we don't love the nights as much as we used to.
Okay.
And it's big teams, it's big money, it's big teams, it's big data. When I went on my first observing run, I brought my data home on a reel-to-reel cassette, which I still have, and I've never been able to read. But yeah, that's, you know, I love that data because I had to, but now it all just comes over the internet. So the sociology of it is different, the philosophy of it is different, but also this idea that very precise, but not so much understanding.
Okay, thank you for your being so concise there. But Ofer, tell us, dark energy differing from this modified gravity that Michaela was talking about. If you could
it's very much related to that point.
Yeah.
So just to put it, we refer to Einstein 1917.
Yeah.
And again, talking about the change. Here's one person using a pencil and a paper, writing a big letter, lambda, and you know, 100 years later, there are billions of dollars, and who knows how many thousands of astronomers trying to figure out this lambda, right? In that equation, you have freedom. You can put it on the left-hand side or the right-hand side, right? It's just like saying, either you write 1 + 1 = 2, or you write 1 = 2 - 1. Both are correct, but they have an entirely different meaning. Different meaning, right? Put left-hand side, it's as if you treat gravity, which where he put it, as far as I remember from the newspaper. Put on right-hand side, you get this vacuum energy that John was talking about, right? So I think our coming to understanding, right? So the fact that we have now the values, certain values to percent level, still requires understanding what does it all mean. And we still don't know whether really it's some kind of constant that at present, with a particular value, generates acceleration of the universe, or maybe it's some energy everywhere. So we don't know that. Now, I'll tell you a secret how scientists work. When something doesn't quite make sense, they make the theory even more complicated. Okay? So instead of just saying, look, we don't know if this lambda is on the left-hand side or right-hand side, They said, let's have a higher level theories.
Does us both?
And there's a whole zoo, of models which come with all kinds of exotic names, which could be, broadly speaking, fall into these categories. It's either part of the gravity or part of some sort of mysterious field or energy. And I think it's great, right? It keeps many people busy in very original ideas, but how do you narrow it down? So I'll just say one more sentence. How nature sometimes is so creative. In August, something really important happened in physics, really important, and that's a discovery of a gravitational wave from a binary neutron star. So in total now 6 events, 5 are binary neutron stars, binary black holes, which are interesting in some ways or boring in another way. This binary neutron star is really interesting. Why? Because you can also detect light coming from the same event.
Yeah.
Now, in just that measurement, in August, 17th of August, I believe, 2017, it was only announced in October, just from that measurement, it's a gravitational wave also predicted by Einstein, they got that right as well. And 1.7 seconds after that, there was a flash of light coming using a satellite and the gamma ray. And then later there was some other light coming, and actually our dark energy survey camera detected the flash. But it's this 1.7 second, and I won't speak for more than 1.7 seconds.
This is a long sentence, but carry on.
It will be a long sentence. Has told us that the gravitational waves move at the same speed as light.
Yeah.
This by itself rules out many crazy models. And I feel sorry for some people who invented them.
I don't.
Okay, just one event, 1.7 seconds, and it's dead. So I think that's the beauty of the subject. That's the beauty, that suddenly there's the
Killer experiment. Observation.
killer experiment that suddenly appears out of nowhere. Maybe other people thought it, I'm sure people. And I think that's the hope, to tell if it's one or the other.
Okay. Right. Three questions, 5 minutes. Right. Now, Michaela amazingly suggested there was only one universe a few minutes ago. Now everyone knows it's a multiverse. So, John, just very quickly, tell us what a multiverse is in the context of what we're talking about.
Do I get 3 minutes?
No, just one universe, 1 minute.
People talk about the multiverse as an act of desperation, because we've measured very accurately all these numbers that characterize the universe, but they make no sense. Let's focus just on one, the energy density of the dark energy. It's this tiny number. If you know what SI units are, it's about 10 to the minus 27 kilograms in 1 cubic meter. Now, if you try and calculate that using the uncertainty principle, quantum mechanics arguments I was waving my hands about earlier, you'd get a much larger figure. Lots of people have tried this, and it's hugely greater. If you take that seriously and ask, well, supposing there'd been much more dark energy than there actually is, what would the consequence have been? The consequence would have been that the gravitational effects of dark matter, the stuff that can clump, would have been negligible. And so astronomical structures, galaxies, stars, down to planets and us, would never have happened. So that makes you think, so how is it that the cosmological constant knew to be small enough to let us exist? And we've been here before. Here we are on the Earth. If it was 10% closer to the sun, we'd all fry. If it was 10% further away, liquid water would be impossible. Either way, no life. So somehow the Earth is just tuned to permit observers. That's a miracle. Or it means the universe is stuffed full of planets at all sorts of distances from their stars, mostly too hot or too cold, and we don't live on those. Well, what a surprise. We only live where we can live. So the idea of the multiverse is that there are actually many copies, but not exact copies, of our universe. Now, where they live, point to them. Let's not get into that in 3 minutes, or indeed 30 probably. But you can imagine that as a possibility, just lots of copies of the universe, some with huge cosmological constants, mostly with huge ones, but just a very few have cosmological parameters, very unusual ones that permit life. Then that would provide an explanation of why the cosmology parameters are as they are. Now, philosophically, this is a big problem. It's abandoning a lot of the principles of testability in science, and a lot of people are very, very unhappy to take this line of reasoning. But the fact is that we have at the moment no other explanation. The cosmological parameters make no sense unless they're dictated to some extent by the fact that we're here observing the universe.
Okay.
And that's what the multiverse is all about.
I can't resist asking, but you might answer this in one word. Do you think the multiverse is now the orthodoxy in cosmology now, or not?
Well, look.
That's all right,
So
one
in
word.
science...
You don't know, right?
No, in physics and astronomy particularly, we work to order of magnitude.
Yes.
All right, so 25% of the universe is in dark matter, 70% is in dark energy. That's the same. So to order of magnitude, about the same number of cosmologists take the multiverse seriously as hate it.
Very diplomatic. All right, Alex, how might dark matter be useful?
Right, so if I had longer, I'd expand on things, but I'd say there's three things. The first one is where it's probably not going to be useful is in terms of an energy source or something like that.
Right.
There's just not, and John mentioned the total amount of dark energy within the sphere of the Earth is something like a microgram.
Milligram.
Milligram. There's just not enough to do much with. The dark matter, I mean, our experiments that we're trying to search for dark matter scattering off stuff, if we instrumented the entire planet with a perfect detector, we wouldn't be able to harvest enough energy to run this in standby mode. So it's not a great power source. How else might it be useful? It's fabulously useful for outreach and public understanding of science. We have events like today, right? And we will fail as a society if we do not encourage and enthuse a new generation of bright minds into science. But then, as a physicist, the thing I'm looking forward to most with dark matter, and perhaps dark energy, is what we've been talking about quite a few times. Kathy started with, what was your opening sentence?
Embarrassment.
It's an embarrassment. And then we've got a catastrophe in terms of trying to understand the scale of dark energy. It just doesn't make sense. We have to resort to crazy, bonkers ideas like multiverses. You can see which side of the argument I'm on, I'm afraid. Dark matter, I think, is we have some theories as to what dark matter might be, and it would, if we can confirm or select one of these theories as being correct by making a direct detection of it, then it may well kind of unlock the next phase in our understanding of truly fundamental physics and how it works. So we've got lots of problems. There's a crisis in cosmology and in particle physics. We don't understand that we have something called the Standard Model. It works really well, but we haven't got the faintest clue why it exists, how it does, why it's got the number of particles and things, why do the forces work as they do, why is there matter in the universe, not antimatter. There's something called the strong CP problem, which is a huge, huge mystery. All of these things, maybe I'm an optimist, honestly, maybe identifying what dark matter is and will take us that next step to start unlocking a lot of these different problems. Right now we have huge problems in many, many areas, despite the fact that we have great precision coming from astronomy. So that's what I think dark matter might be useful for, unlocking the next phase in science kind of thing.
Okay, you mustn't be given the short straw because you're last, so we'll allow you to run over a little bit.
No.
Just very briefly, just if you would just give a philosophical perspective on what this might show about realism and progress, just briefly.
Sure, yeah. Well, I think there is no doubt that cosmology has progressed tremendously over the past century and really 30 years. We've just heard that until 30 years ago, it's the kind of standard view to assume dark matter and dark energy now is. And if you look at, from a technological point of view, the existence of dark energy surveys or the new generation surveys, I think it's really a clear evidence of a huge success in terms of becoming more and more precise in gathering data. Are dark matter and dark energy real? obviously the smoking gun in physics would be to find particles that confirm the existence of dark matter, a sort of experiment that Alex is involved in, when the dark energy is able to provide us more precise data about the nature of dark energy. But to me as a philosopher, I think the success of a jigsaw puzzle, not so much in finding the last missing piece of the jigsaw, but more with a kind of compelling image coming out of the jigsaw puzzle. At the moment we have a compelling image that tells us we have reasons for believing that there are those objects. So until and unless a better theory comes forward that is able to be as successful as the current one, regardless of whether or not we find the direct evidence for dark matter and dark energy, I think this will remain the orthodoxy.
Okay. Right, thank you. Thank you for your concision on that second part here. I just wanted then to just thank our panel, in particular Michaela, who actually set this evening up and invited us all. I'm very, very grateful for that. And also, we heard it mentioned, the European Research Council. This is actually funded by a grant under the heading of Perspectival Realism. Now, if you don't know what that means, you can read it on here. There's a panel here. But I would just like, if I could, in the last 60 seconds or so, just a little bit of perspective, not necessarily realism, but just a bit of perspective. Because I began by with a prediction made here in Edinburgh that cosmology was probably going to be the most revolutionary development of the 20th century. And there's just a couple of points, one of which was alluded to actually here earlier on, which I think underlines that. For anyone who thinks that, who watches their Horizon programs and sees 9 decimal place agreements with the magnetism and spin of muons or what have you, you think how incredible it is that we have theories that are so accurate about these small particles. Just let me say that if you actually go back and use quantum theory and relativity, right, and you calculate the energy of empty space using those celebrated theories, quantum theory, relativity, you use them to calculate the energy of empty space on the back of an envelope, which you can do if you're a good graduate student, you find that your answer disagrees with the cosmologists. How much by? Factor of 2? Factor of 4? Factor of 10? Factor of 100? No. By 120 orders of magnitude. It is wrong by a trillion. Now, that, in the words of the great quantum physicist Nima Arkani-Hamed, right, is probably the most inaccurate prediction ever made in the history of science. That is the state of our physics at the moment. And Nima added a point when I said to him, so how do we understand the macroscopic universe in terms of quantum theory? And he said, I have no idea. That is the extent of the puzzlement at the heart of physics. And I think our panelists tonight have given us a sense that there is still so many adventures ahead before we could really say we understand this order at the heart of the universe. So thank you very much, ladies and gentlemen. Thank you.